morning, students. Let me continue with process synchronization. In the last class, we had discussed about semaphores and how a semaphore could be used to address the issues in some of the classical synchronization problems, like bounded buffer problem, dining philosophers problem, readers writers problem. And we have seen that semaphore for some of the issues, semaphore could become perfect solution, yeah, but it could also lead to an issue called deadlock when it is not appropriately used, or by its very nature it could lead to deadlock. So therefore, there is one more synchronization tool that is called monitors. In today's lecture, I will be discussing about monitors. Let me first tell you some of the aspects of monitors. Please don't worry if you don't understand. I'll be explaining the concept of monitors with an example. Okay, so basically what you need to understand is that monitor is a programming language construct. So it should programming language should support monitors. It is like an abstract data type which encapsulates private data with public methods to operate on that data. It is something like class. Like you have private data surrounded by public methods, something like this, public operations or public methods, and outside world or other threads or other processes uses these methods to access private data, right? So it is something similar to the concept of class that we have in some of the programming languages, object-oriented programming languages, right? Here, a monitor has to ensure that only one process could live in a monitor. That means when one process is accessing the monitor, or accessing the shared variable through the operations defined in the monitor, no other process can do the operation or do some other operation on the shared variables. So this is what is all about monitors. Now let's see the structure of a monitor, and let us also schematically represent the monitor. Okay, a monitor actually looks like this. This is a programming construct, or you can say reserved word monitor, and this is a user defined name to the monitor. And inside the monitor you can have a list of shared variable, or you can define shared variables, and there are something called condition variables. I'll explain what condition variables are. Okay, see, once the shared variables and condition variables are defined, we can have several definitions of the procedures. Like here I've shown procedure P1, P2 to Pn. So there could be several operations defined. These are the operations that are performed on these shared variables, right? And there is a special initialization code when the monitor is invoked. The initialization code is run first. Okay, whatever you have written inside the initialization code gets executed first. Okay, so that's how a monitor looks like. Okay, a programmer who needs to write a tailor-made synchronization scheme can define several condition variables. Now, as the name indicates, X is a condition and Y is a condition. The processors can wait on these conditions. For example, a process wants to wait on condition X, then it can do so by executing this operation. Okay, and any process, when the event occurs, any process can perform the operation signal and X dot signal means that if any process is waiting on the monitor X, or sorry, condition variable X, it can resume its operation. That's the meaning. So don't get confused by the definitions that we gave to wait and signal when we discussed about the semaphore. Here wait means whichever process executes this will simply get into the waiting mode, or it goes into the waiting queue and it waits on this condition X. I have shown that schematically in the next slide. And whichever process executes this signal will release a process from this waiting queue. That is if this condition occurs. Meaning is that this condition has occurred and one of the processes from the waiting queue is released. All those processes are waiting on this event X. Okay, so that's the meaning. And if no process is found in the waiting queue, that is if zero process is found in the waiting queue, even then the execution of this signal operation will not harm the harm the program execution. Okay, that you'll have to keep in mind. So these wait and signal operations which I am talking about here are completely different from the wait and signal operations that we talked about when we discussed about semaphore, right? Now let me show you the schematic representation of a monitor. Bear this structure in mind and then look at the schematic representation which I am going to show you now. Okay, whatever I have told you verbally, the same thing has been shown here visually, right? Now you have shared data. This is a monitor. This oval shaped thing is a monitor. You have shared data and have condition variables. Here there are two condition variables and some of the processes are waiting on those condition variables. There are three processes waiting on condition variable X and there are two processes waiting on Y. So that means when the condition X occurs, some process will do a signal operation on X which will release the process which is waiting for the condition X. So in general, what is shown here, these 5 processes which are waiting, okay, over this monitor. And there are several operations defined inside the monitor. Every process uses these operations to access the shared data. One of these operations to access the shared data. And the initialization code, this is a code, a segment of code which gets executed when the monitor is invoked. So please remember, in a nutshell, monitor is a synchronization construct which is supported by the programming language, and inside the monitor you will be defining the shared variables or shared data, and if required some conditions or condition variables. Then you will be defining several operations that could be performed on the shared data and initialization code. The multiple concurrently running threads or concurrently running processes can access the shared data through these operations which are defined inside the monitor. I hope this is clear. Now let us take the example of dining philosophers problem that we discussed in the yesterday's class. So what did we discuss about dining philosophers problem? So let me change the slide, go to the slide. Let me see whether that slide is there. And we will recall whatever we had discussed about the dining philosophers problem in the yesterday's class. And now, and look at a deadlock-free solution given by the monitor to the dining philosophers problem. Okay, this is what we had looked at in the last class. There are 5 philosophers and there are 5 chopsticks. So there is a serious, shortage of chopsticks for these philosophers to eat, and you have to ensure that when somebody is using a chopstick, the other philosopher cannot use it because it is a shared chopstick or shared resource, right? And we looked at a solution. Let me show you that solution also. So we saw this solution. Unfortunately, here we allowed the philosophers to pick up the chopsticks one by one. It could be the chopstick which is to the left, or it could be the chopstick which is to the right. Okay. If they are free, then the philosophers can pick up those, yeah, pick up those chopsticks and wait for getting the other chopstick. What is the issue? Now, there could be a situation where every philosopher could be having one of the chopsticks. That is, P1 could have this chopstick 2, and P5 could have this 1, and P4 might be holding this 5, and P3 could be holding this chopstick 4, and so on. This is a there is a circular weight. Okay, that is P1 is waiting for a chopstick which is held by P5, and P5 is holding, is waiting for a chopstick which is held by P4, and so on. So there is a circular weight. So, and every philosopher refuses to release the chopstick because they have not yet finished eating. So they don't release the chopstick, and everybody is holding one chopstick, right? So this leads to deadlock. That's what we discussed in the last class. Now, what could be the solution? The solution could be you have to make the philosopher to drop the chopstick if he fails to get the other one. So that means, what you're supposed to do, you put a constraint that if a philosopher fails to get both the chopsticks to eat, then the philosopher drops the chopstick which he is holding so that the other philosopher can eat. This could be the solution. This is what is the solution which we have given to dining philosopher problem through the monitor. Let's have a look at it. Okay, let me first write the monitor or define the monitor. Monitor, this is a reserved word, I cannot change it. I have used a name for this monitor, DP as the name for this monitor. Okay, what I have done inside the monitor, there is an enumerated uh, elements inside an array state of 5. So there are 5 elements, and each element could take on any one of these values. Okay, state of 1 could be thinking, hungry, or eating. State of 2, okay, state of 2 could be any one of these. For example, it could be eating. Okay, like that. So this is what is enumerated data type, which I am very sure that you have studied in one of the programming classes which had taught you programming languages like C or C++. So I'll not be spending time explaining you what is enumerated data type, right? Next is what, so let me clear this. I have defined condition variables. How many condition variables are there? 5 condition variables. In fact, it is an array having 5 elements. So any process can wait on these conditions, right? So let you first try to understand the statements which are there in the monitor. Then we will see how this monitor could be used. So this is the first procedure I have inside the monitor, and this is another one more procedure I have inside the monitor. I have one more procedure which I put in the next slide. I will show you. Now this procedure is for picking up the chopstick. When the philosopher wants to pick up the chopstick, he will execute this pickup, right? What is passed to this procedure is the philosopher's number. Let's assume that way, okay? So this state represents the state of the philosopher, okay? The philosopher could be thinking, he could be eating, or he could be hungry. Of course, when he becomes hungry, he will start eating, right? So in the pickup, we are making state of I, state of that philosopher hungry. Okay, that is why he is trying to pick up the chopstick. So we are going to make his state hungry. Then I execute a procedure testify. I will explain that later. So when I pass the control to this procedure, I should be allowed to eat, or philosopher should be allowed to eat if chopsticks are available, and the state should have been, philosopher state should have been changed to eating. So I test that here. If the state of the philosopher is not changed to eating, if it is still hungry, it means that the philosopher has failed to get the chopsticks after this test. I hope you understood this. Let me repeat. In the pickup, what I am trying to do, because the philosopher has shown the interest to eat, I am making his state as hungry, and then I test whether he could get both the chopsticks for eating. That is what is the information I get from this test. After that, I check the state of the philosopher. If it is not eating, that means the philosopher has failed to get the chopsticks to eat. So what do? I make the philosopher to wait by executing self of I, where I indicates the philosopher's number, right? That itself is the condition. So he will be waiting for getting the chopsticks, right? So that is what is pickup. Let me clear all this. Now let's look at this put down. So after philosopher completes eating, then he puts down the chopstick. Okay, both the chopsticks. So he passes on the chopstick. Okay, who is the philosopher who is trying to put the chopstick down? That is indicated by this variable I. For example, if it is the philosopher 5 who is trying to put the chopsticks down, then the value of I will be equal to, this will be the value of I, right? 5 will be the value of I. Now he has finished, the philosopher has finished eating. After he eats, in the last class we had discussed that the philosopher does only two things, either eats or thinks. Because the philosopher has finished eating, he is trying to put down the chopsticks. So therefore, the state of the philosopher is made thinking, right? It is made thinking. Now this philosopher who is putting down the chopsticks, he is putting down two chopsticks, tests if somebody is waiting on those, waiting for those chopsticks, right? So why is it I plus 4 modulus of 5, I plus 1 modulus of 5? That I will tell you. This 5 because there are 5 philosophers, okay? So if you we will again go back and see that diagram. Okay, see this diagram. Now if this philosopher P5 is trying to put down, what are the chopsticks that he is trying to put down? It is 5 and 1, which could have been useful to philosopher 4 and philosopher 1. So he is trying to tell P4 and P1 that he is putting down the chopsticks. So how will you find the neighbor of P5? He is a neighboring philosopher. He is also a neighbor to P5. So how to find that? 5 is the philosopher's number. You add 4 to it. It becomes 9. 9 modulus of 5 is what? It is equal to 4. So this is the number of the philosopher who is either sitting right or to the left of this philosopher, okay? P4. Now how do you find another neighbor of P5? 5 plus 1, that is equal to 6 modulus of 9. 6 modulus of 9. 6 modulus of 5. There are 5 philosophers. I am very sorry, okay? 6 modulus of 5. What is that? That is 1. So P1 is the philosopher who is sitting to the other side. So we are successful in finding who are the neighboring philosophers to this P5 who is trying to put down his chopsticks. Okay, so what he does is he checks whether one of his neighbors is waiting for chopstick which was held by him to eat, and he also tests whether the other neighbor sitting to the other side of him is waiting to get the chopstick for eating. That's what is done in put down. I hope you understood. In pick up, we change the state of the philosopher to hungry, test whether the chopsticks are available. If available, eat. Okay. Otherwise, wait. While putting down, change the state of the philosopher to thinking because he has finished eating, and check to see whether any of his neighbors are interested in eating and waiting for the chopsticks held by the philosopher who is putting them down now. Okay. Okay, now you see an interesting procedure that is also present in the monitor, which checks whether the chopsticks that a philosopher is trying to get are available or not. Now I told you why I4 plus modulus of 5. This is to get the neighbor. For example, now as I told you, the philosopher 5 is a one who is testing. Okay, so we have to make sure that philosopher 4 is not eating and philosopher 1 is not eating, because they are the neighbors of philosopher 5. How to make sure? We will check state of I plus 1 modulus of 5, that is 4, is not eating, and state of I plus 1 modulus 5, that is philosopher 1, is not eating, and this particular philosopher is hungry. Of course, before passing the control to this procedure, we would have made his state hungry. So if all these conditions are met, then this fellow or this philosopher is allowed to eat, because if he is eating, then one of the chopsticks that P5 wants is with him. If he is eating, then one of the chopsticks that he wants is with him, so he cannot proceed to eat. So therefore both the chopsticks should be available. That's what is tested in this procedure. So there is signal here, that is, after this philosopher finishes eating, he can allow another philosopher to eat who is waiting. Okay, who is waiting, right, for the chopsticks which are held by this fellow. That's what is done in the test. I hope you understood. Okay. Okay, there is one more initialization code which I had told you. Initialization code is part of the general structure of the monitor. What we have written here is, initially we initialize the state of all the philosophers to thinking. That's what is the initialization code. Now we have defined the monitor. Now let's see how the philosophers can utilize the methods or the operations that you have defined in the monitor in a mutually exclusive manner. Okay, what are the operations that we have defined inside the monitor? Pick up and put down. And what is the shared variable which we have defined inside the monitor? The shared variable are those chopsticks, right? Okay. Now you see, any philosopher, here DP represents one of the philosophers. Okay, philosopher in this case is a process. So any philosopher who is trying to eat will pick up. For example, let's say the philosopher 5 is trying to eat. Now what happens when he executes this? Where the control is taken to? It is taken to let me just show you that code. Okay, so that control is taken to this pickup. So what is done here? State of 5, because the philosopher 5 is trying to eat, is made hungry, because he is the one who has you know um, uh, who has done this operation, pickup operation. Now what is tested? The philosopher who is to the left of him or to the right of him are not eating. That is what is tested. If they are not eating, he is allowed to test without executing these two statements. Otherwise, if one of those philosophers are eating, then he is not allowed to go to the critical section, that is eating, right? This is what happens. Okay, after he successfully picks up both the chopsticks that he needs, that is here we're talking about philosopher 5, then he eats. After he eats, he puts down the chopsticks. While putting down, what we have written in this put down operation or procedure, let's see. Okay, what we have written here, so the philosopher has just finished eating, so we have made his state thinking, and we allow, or the philosopher 5 allows one of the philosophers, or he checks any of the philosophers sitting to the left of him and to the right of him, if they are waiting for the chopstick that he was holding till now to eat, uh, they can, he will signal, that is we have written here, I'll just show you, I'll go to the next slide. Okay, see here, he will execute the signal operation so that they can come out of the waiting queue and grab the chopsticks and go and eat. Okay, this is the deadlock free solution to the dining philosopher problem. Why we have avoided deadlock? We have not allowed the philosophers to pick up one chopstick and wait. If they have to eat, then they have to pick up both the chopsticks. If any one of the chopstick is not available, that means they have to wait till that chopstick is released by the neighboring philosopher. That's the solution. So, and there is no deadlock. But there could be starvation. That means the same philosopher could again and again, he can drop the chopsticks and pick up the chopsticks again, and see the chopsticks are free, pick up the chopstick again, and could go into the critical section, that is could start eating. So there could be starvation in this kind of a solution. So what you'll have to think is that providing a solution which is starvation free. So thus we have discussed several techniques to handle the synchronization problem that could occur when multiple cooperating processes run concurrently. So with this I have completed module 2 of your syllabus. Let me go to the next module, that is module 3, and discuss about deadlocks, characterization of deadlocks, different techniques to handle the deadlocks in that module. Thank you. Okay, I finished talking about several CPU scheduling algorithms and process synchronization techniques. I'll move forward and discuss about deadlocks. So before I proceed, I want you to recall that a computer system has a lot of resources that are to be distributed among a number of competing processes. These resources are CPU, there could be one or multiple CPUs, files, IO devices like printer, hard disk, DVD drive, memory space, etc. So there could be multiple CPUs, as I told you. Suppose if you have two CPUs in the computer system, then we say that there are two instances of CPU. So similarly, suppose you have 5 printers connected to the computer system, we say that there are 5 instances of resource type printer. Okay, so such resources should be allocated or distributed among the processes which are competing for these resources. Now, any process, if it has to get a resource, then it has to first request for the resource. So let's go to the next slide and see. Let me clear this. Let us go to the next slide and see if any process has to utilize the resource, then it has to first request for the resource. If the resource is available, then the resource is allocated to the requesting process. If the resource is not available, then the process which is making the request has to wait till the process which is holding the resource releases the resource. Okay. Once the process gets the resource, it operates on that or uses it. For example, printer is the resource that a process has requested for, and it gets the printer. After it gets the printer, it prints or it uses the printer. Once it is done, it releases the printer so that some other process could utilize this resource. Okay, so that's how resources are requested, used, and released. Okay, now let's see what is the issue. In the process of distributing the resources among the computing processes, there could be an issue. Let's see what is that issue. We have already discussed about this issue. Let me state the issue once again and see how this issue could be tackled using several techniques. Okay, this is the issue we have already discussed when we discussed about the semaphore. Let me again define the distribution of resources among the processes which are running in the system concurrently. There could be this situation, deadlock situation. Let us first define deadlock. A set of processes is in a deadlock state when every process in the set is waiting for an event that can be caused only by another process in the set. So in case of semaphore, we have seen that if some process acquires a lock on a semaphore S, and some other process, let's say process P has obtained lock on semaphore S, and another process has obtained lock on another semaphore Q, let's say process P1, this is process P0, and this P0, if it also wants uh, resource Q, okay, this can be, semaphore could be called as logical resource, unlike the devices which are called as physical resources. And similarly, P1, after acquiring the lock on Q, it could wait for S. So P0 cannot proceed unless P1 releases this S, releases lock on S, and P1 cannot proceed unless P0 releases lock on S, and P0 cannot proceed unless P1 releases lock on Q, right? So this is what we had discussed when we discussed about semaphore. I think it is clear. Did I say that correctly? P0 has obtained lock on semaphore S and waiting for semaphore to get the lock on semaphore Q. P1 has obtained the lock on Q but waiting for getting the lock on S. So P1 and P0 are the waiting processes. P0 is waiting for an event that has to be caused by P1, and P1 is waiting for an event that has to be caused by P0. So now we are in a deadlock state because P0 will not do signal on S unless it gets Q, and P1 will not do signal on Q unless it gets S. So therefore there will not be any progress and the system halts. So this situation is known as deadlock. This we have already discussed. So let me clear this and give you one more example which is relevant to this context. So that is if you assume that the system has 3 CD drives. Okay, that means there are 3 instances of CD drives, and suppose let us also assume that there are 3 processors in the system, and each of 3 processors holds one of these CD drives. That means every process is holding a CD drive. And let us assume that these processes, to complete their execution, they might need one more CD drive. Okay, so if each process now requests another drive, the 3 processes will be in a deadlock, right? Because the processes will hold one of the CD drives and makes a request for another CD drive, so that it will the process will not get, because all the processes in the set are waiting. So that's what is known as deadlock. I hope you have understood. If you have not got this clearly, I will take many more example during this lecture, and try to make this concept very clear. Okay, so let's try to characterize the deadlock. For deadlock to occur in a system, there are some necessary conditions. So what are those necessary conditions? One is mutual exclusion. Okay, what is mutual exclusion? That is, suppose there is a resource, let's say printer. Okay, so this printer is not shared by multiple processes at the same time, in the sense that if process P0 uh, gets this printer, okay, so this printer cannot be used by another process P1, though it needs this printer to complete its execution. That's what is mutual exclusion. P0, process P0, the usage of this printer among these processes P0 and P1 is mutually exclusive. Okay, only one process at a time can use the resource. If another process requests that resource, the requesting process must be delayed until the resource has been released. Okay, so if P0 is using the printer and P1 requests for it, P1 has to wait till P0 completes its operation with the printer and releases it, right? So that's what is known as mutual exclusion. So there has to be mutual exclusion. This condition has to be satisfied, and there has to be hold and wait. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. So that is, P0 is holding some resource R and it is waiting for some other resource R1 which is held by, let's say, P1. So this is called as hold and wait. That is, this P0 is holding resource R and it is waiting for R1. So this kind of situation has to be there in the system for deadlock to occur. Okay, there are two more necessary conditions for deadlock to occur. We will discuss about those two conditions, right? Okay, the next condition is no preemption. Resource cannot be preempted. That is, the resource can be released only voluntarily by the process holding it after that process has completed its task. So that means a process holding a resource, let's say a process is holding hard disk and there is only one instance of the hard disk. So you cannot, let's say P0 is holding it and P1 makes a request for this resource. Now you cannot preempt in the sense take it away from P0 and give it to P1. That is preemption. That is not permitted. Okay. So In that kind of a scenario, deadlock can occur. The last condition, but very important condition, which leads to deadlock is circular weight. Okay, this is we have already discussed this circular weight when we discussed about dining philosopher problem. Let us recall that once again here. So there we said that no, we had in that problem we had considered some five philosophers, dining philosophers, and all of them uses the chopsticks which are kept to the left and right of them to eat. Now P naught holds a chopstick and waits for a chopstick which is being held by P1, right? And P1 holds a chopstick. Chopstick is the resource here, right? And P1 holds a chopstick and waits for the chopstick which is held by P2, and P2 is waiting for a chopstick which is held by P4 and so on. So we have a situation called circular weight. Okay, that's what is been explained here. A set P naught to Pn of waiting processes must exit such that, so these are all waiting processes now. P naught is waiting for a resource held by P1. P1 is waiting for a resource held by P2, so on. Pn minus 1 is waiting for resource held by Pn, and Pn again no, is waiting for the resource held by P naught. So therefore there is a circle, okay, or there is a cycle. You can call this as a cycle or circular waiting. These are the necessary conditions. If all these conditions are met, then there is going to be a deadlock in the system. What are these necessary conditions? Let us quickly recall. One is mutual exclusion. What is mutual exclusion? A process uses the resource in a mutually exclusive manner. That means when one process is using the resource, no other process can use that resource. That is mutual exclusion. And the second necessary condition is hold and wait. A process holds a resource and makes a request for some other resource which is being held by another process and waits for that resource, okay, till that resource gets released. This is called hold and wait. And the third necessary condition is no preemption. If a resource is being held by a process, the process will not release that, okay, until it is done with that resource. So it has to voluntarily release that resource. It cannot be forcefully, the resource cannot be forcefully taken out from that process and given to some other process, which is known as no preemption. Okay, circular wait is the last and the important condition. That is, the processes will be waiting for the resources being held by other processes in a circular wait manner. That is, if there are five processes, P naught is waiting for P1, P1 is waiting for the resource held by P2 and so on, and P5 is holding for the resource which is being held by P naught. So that's called as circular wait. Okay, if all these conditions are met, then there is going to be a deadlock. Okay, so before we discuss about the techniques to handle deadlocks, let us discuss about an important data structure called resource allocation graph, which is a directed graph which helps us to visualize the deadlock. This graph consists of a set of vertices V and set of edges E. Normally graph will have vertices and edges connecting these vertices. So here also resource allocation graph is going to have vertices and edges connecting them. Okay, so and these edges are directed edges. I will explain you what the direction means in the next slide. And further, these vertices are divided into two different types: vertices representing the processes and vertices representing the resources in the system. Okay, so this set representing all the resource types in the system, right? And resource allocation graph will have two different types of edges. So before we proceed, let me show you the notations used for representing vertices. A circle is the notation used for representing a process. Okay, and this rectangular box is what is used for representing a resource. Let's say R0 is a resource and P0 is a process, right? Now, if there is a request from P0 to get the resource R0, so there has to be an edge between this circle and this rectangle, which shows that a process is requesting for a resource, right? Now you have to put a dot inside this box. If you put a single dot inside this box, it means that there is one instance of resource type R0. Okay, now this edge is called as request edge because P0 is making request for R0. So it could be the other way also, that is the resource, that is R0. If this is a resource R0, so let us assume that this R0 is being held by P0. So if that is the case, then this kind of an edge is called as assignment edge. Okay, if the process is waiting for the resource, that is depicted like this, and this edge is called request edge. If the process is holding a resource, then there will be an edge from the resource to P0, but the arrow is towards the P0. So this kind of an edge is called assignment edge. Now before the resource is allocated to the process, you will find request edge, and once the resource is allocated to the process, the same request edge becomes assignment edge. So these things you'll have to remember. Now one more thing that you have to remember is, like I told you, that a resource is represented by a rectangle, and instances of uh, that kind of resource is represented by putting dots inside this box. For example, if I put 3 dots inside this box, it means that there are 3 instances of resource type Ri. Okay, so these are some of the notations that are used in the resource allocation graph. Okay, in a nutshell, what is a resource allocation graph? The resource allocation graph will have edges. So these edges are processes and resources. Vertices are processes and resources, and these edges are these vertices are connected by edges. So there could be two different types of edges: request edge, when the process makes a request for a particular type of resource, so there will be a request edge between them. If a resource is allocated to the process, then there will be an assignment edge between resource and the process. So now let's look at the resource allocation graph and try to understand what that resource allocation graph represents, right? Okay, now you see this resource allocation graph. Now you have to tell me what all can be inferred from this resource allocation graph. Now there are it says that there are 3 processes: P1, P2 and P0. Okay, further it says that there are 4 different types of resources: R1, R3, R2 and R4. and there is one single instance of type R1, single instance of R3, there are two instances of R2, and there are three instances of R4, right? Now there is an edge from P1 to R1, which means that the P1 is waiting for R1, and this R1 is held by P2. Okay, R1 is held by P2. And similarly, there is an edge from R3 to P3. This is an assignment edge, whereas this edge is a request edge, right? This is an assignment edge. This is an assignment edge. So R3 is allocated to P3. So what kind of edge is this from R2 to P1? This is an assignment edge. One of the instances of R2 is allocated to P1, or P1 is holding one of the instances of R2. So similarly, this is also an assignment edge. One of the instances of R2 is held by P2. Okay, and these resources, or resources of type R4, these are not being used. Okay, now hope you have understood what is a resource allocation graph, and now we will see what is the use of this kind of a resource allocation graph. Okay, see, you can look at this resource allocation graph, and if there is a cycle present in this kind of resource allocation graph, we can say that the system is in a deadlock state, or the processes which are part of that cycle are in a deadlock state. But whereas here you will not find a cycle, because see, you see it goes in this direction, but this is in a different direction, this is in a different direction, so there is no cycle. There is no cycle means that this P3, after it completes using this R3, it is going to release this R3, which will be used by P2. It is already holding R1, so therefore all its requirements are met, so it completes its execution and releases this R2. Okay, or it releases this R1, sorry, releases this R1 and maybe R2 also, and P1 has one of the instances of R2 and gets R1, so it can also complete. So in what order these processes will be completing their execution? First P3 will finish, because it wants only R3 and it has R3, so it will finish, and next R3 is released, so P2 has R1, it has R2, R3 is released, so therefore P2 can finish, and after that P1 can finish. So there is progression, therefore in this case there is no deadlock. So if you find a cycle in the resource allocation graph, then you have to suspect that there could be a deadlock. Okay, I don't have much time. I'll quickly discuss about this and stop. Necessary and sufficient condition, okay, for deadlock to occur. Now you look at this graph. This is a resource allocation graph. What do you infer from this graph? P1 is requesting for R1. One of the instances of R1 is held by P2, and other one is held by P3. And P3 is making request for R2. One of the resources is held by P1, and other is held by P4. Now there is a cycle. Yes, if you look at this diagram carefully, so there is a cycle, right? See, there is a cycle. And who are all participating in the cycle? P1 and P3. Can we say that these two processes are in a deadlocked state? No. So just mere presence of the cycle in the resource allocation graph cannot guarantee that there is going to be a deadlock. So that's why we say that this is a necessary condition but not sufficient for deadlock to occur. Why is that? Because you see here this P4 has an instance of R2, so after some time it will release this R2 because that is the only resource that it wants. So it will release this R2, and this R2 will be used by P3. It is given to P3, and P3 now has R1 and has an instance of R2, so it can complete. P4 completes first, P3 completes and releases R1, which can be used by P1, and P1 can also complete. P1 can also complete, and P2 can also complete because it just needs R1 and it has R1. So there will be progression and there will not be any deadlock. But you look at this, okay, here there is a cycle. Let us only take this one, okay, this cycle. Okay, there is a cycle like this. Now what happens is, now you observe carefully, this P1 is waiting for R1, which is held by P2, and P2 is waiting for R3, which is held by P3, and P3 is waiting for R2. Though R2, there are two instances of R2, both the instances are held by two processes, that is P1 and P2. So P2 to complete, R3 has to be released, but to release R3, P3 has to get R2, and to release this R2, P2 has to get this R3, or P1 to release this R2, P1 has to get R1, but that is being held by P2. So there will not be any progress at all in this case. So therefore we can say that there is a cycle, and this cycle is a necessary and sufficient condition for deadlock to occur. Okay, so I hope you understood this. Just mere existence of cycle will not guarantee deadlock, but it could lead to deadlock. That's what we have discussed here. It depends on how many instances of particular type of resource we have. Okay, so I hope you understood. Resource allocation graph is used to visualize a deadlock condition. Okay, so let me stop here and I'll continue discussing about deadlocks in the next class. Thank you.